The unit vectors I, j, and k are special in that any vector in R3 can be decomposed as a combination of these three. So it can be written uniquely as a combination of I, j, and k. Now, any set of vectors that has this property, or any vector can be written as a unique combination of these, is called a basis. To delve into this in a little more depth, to actually rigorously define basis, we need a few definitions first. The first is the idea of a linear combination. So we say a linear combination of a set of vectors, let's say v1, v2, up to vn. So a linear combination is any vector of the form a1 v1 plus a2 v2 plus and so on up to an vn. So this should look kind of familiar, is that this is just a linear function of those vectors. So if it can be written as a linear function, then it is a linear combination. So for example, is the vector 1, 2, 3 a linear combination of the set 1, 0, negative 1, 1, 2, 3, negative 1, 0, 1? Well, first thing to note is that 1, 2, 3 is actually one of the vectors in the set. So it's pretty easy to form a linear combination because we can take one of these and 0 of everything else, and that'll give us 1, 2, 3. So 1, 2, 3, if we were to write that out, that's 0 times the first vector plus 1 times the second vector plus 0 times the third vector. So that gives us 1, 2, 3. So yes, it is a linear combination. But the first vector and the third vector are inverses of one another. So we didn't need there to be 0 here. We could have said just the same, that this is 5 times the first vector plus 1 times the second vector plus 5 times the third vector. Well, that also, because the first and the third cancel, that also gives us our goal vector 1, 2, 3. So this says that this combination is not unique, that there's more than one way to write this vector as a linear combination of these three. So with that idea in place, I'm going to talk about the notion of span. So we say that a set v1, v2 up to vn is a spanning set of a vector space V if every vector in V is a linear combination of our set v1, v2 up to vn. So in other words, you can think of this v1 through vn as a sort of way to reconstitute every vector in your vector space. So, for example, let's see if some sets are spanning sets. Suppose we have 2, negative 3, 1, 5, 1, 1, and negative 3, 6, 7. If we want to know if this is a spanning set, so does this set right here span R3? Well, if it spans R3, that means that any vector in R3 must be a linear combination of these three vectors. So let's take a generic vector in R3. So let V be in R3. That means it has components, v1, v2, v3. And we must be able to write this as a combination of these three vectors. So it must be a1 times the first vector plus a2 times the second vector plus A3 times the third vector. And we write this out, we're going to get a system of equations. All right, if we look at the first components here, we've got 2a1 plus 5a2 minus 3a3 equals v1. This is our A column, our A1 column, our A2 column, our A3 column. If we look at the second components, we've got v2 equals, well, negative 3a1 plus 1a2 plus 6a3. That's our second equation. And our last equation, we're going to equate the z components together. So we've got v3 equals 1a1 plus 1a2 plus 7a3. So if you look at what we have here, the first column of this matrix is the first vector of our alleged spanning set. The second column is the second vector. The third column is the first vector. Now we want to row reduce this to see if we actually have a solution. So what we can do is multiply the first row by negative 2 and add it to the first row. So we've got a 0 here. Negative 2 plus 5 is 3. Negative 14 plus negative 3 is negative 17. And then negative v3 plus v1 is v1 minus 2v3. Okay, we can do the same thing with the second row. We can multiply the bottom row by 3 and add it to the second row. So 3 plus negative 3 is 0. 3 plus 1 is 4. And then 21 plus 6 is 27. And then finally we take 3v3 and add it to v2. So we've got v2 plus 3v3. And the bottom row can just sit. 1, 1, 7, v3. Okay, well, first up, we want to make this in row reduced form. So let's rewrite, we'll put the bottom row on top, 1, 1, 7, v3. And just to make sure we've got a leading 1 here, let's multiply the first row by negative 1 and add it to the middle row. That leaves us with 0, 1, and then 17 plus 27 is 44. And then if we add negative 1 of these v's onto this row, we've got negative v1 plus 3v2 plus 3v3. And then we can just move the top row to the bottom row. So 0, 3, negative 17, v1 minus 2v2. So this is where we are so far. And we can clean this out by multiplying the middle row by negative 3 and adding it to the bottom. So this gives us 117 v3. And then our middle row is 0, 1, 44, and then this mess of v's. And now in the bottom row, remember we multiply this by negative 3 and add it to the bottom. So we've got 0, 0. And then we've got negative 132 minus 17 is negative 149. And then we add this negative 3 of these to the bottom row. So we've got 4v1. Now we've got negative 9 minus 2 is negative 11 v2 minus 9 v3. And now at this stage we could divide the bottom row by negative 149 and then employ back substitution. So that just says, since we didn't get a row of zeros here, that yes, we're able to form any vector v1, v2, v3 as a linear combination of vectors from our set. So it spans all of R3. So that's the idea of a spanning set. There is a theorem along these lines about spanning sets that can take a little bit of the headache out of this. Is that if V1, let's actually just write this as a set. If S spans Rn, then S has at least n vectors. So just as an example of this, suppose we're asked the question, does 101, 321 span R3? And the answer, the real quick answer to this is no. There are not enough vectors. There are only 2 vectors in here, which isn't enough to hit all 3 dimensions of the space. To think about what this theorem means, if we have only 1 vector in this space, if we take any linear combination of a single vector, that's just going to give us a line pointing in the direction of the vector. So we can think of this as we start out, we point in the direction 101, and then we take any multiple of this. So we've got a line's worth of values. Imagine that's straight. We've got a line's worth of values pointing in this direction. So those are the linear combinations of the first vector. If we add on to that any scalar multiple of the second vector, that just says at any point in the first vector, we look in the direction of 321 and move along that line as far as we'd like. Well, this gives us a plane, something 2-dimensional. So something 2-dimensional does not fill all of R3. There's only 2 vectors in here, so the span is only 2-dimensional, doesn't span the full space. So the second idea we need to develop the notion of basis is the idea of linear independence. So we say a set V1, V2 up to Vn is linearly independent if C1V1 plus C2V2 plus up to CnVn equals 0. So we have this system of equations right here is only satisfied by all the c's being equal to 0. So we can see that no matter what vectors you take, if you multiply them all by 0 and add them up, you do get the 0 vector. But being linearly independent says this is the only way that happens. So let's look at a couple examples of this linear independence. So first up, let's say we've got the set 110, 101, and 011. So the question is this set linearly independent? Well, let's look at the definition. This says that C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 0. Well, this gives us a system of equations. If we were to write this out, this says that if we look at the x component, the first component here, we've got 1c1 plus 1c2 plus 0c3 equals 0. 1, 1, 0, 0. If we look at the y components, we've got 1c1 plus 0c2 plus 1c3 equals 0. And if we look at the z components, we've got 0c1 plus 1c2 plus 1c3 equals 0. And then we can row reduce this. Or we can multiply the top row by -1 and add it to the middle row. So if we multiply this by -1 and add it to the middle row, we've got 0, -1, 1, 0. And the bottom row can just sit there, 0, 1, 1, 0. Okay, to row reduce this more, we can now take the middle row and add it to the top row and the bottom row. So if we add it to the top, we've got 1, 0, 1, 0. If we add it to the bottom row, it gives us 0, 0, 2, 0. And then let's multiply the middle row by -1. So this gives us 0, 1, -1, 0. Okay, and then finally we can divide the bottom row by 2. If we divide that by 2, it'll just put a 1 in this spot. And now we can add the bottom row to the middle row. That'll leave us with 0, 1, 0. And if we add negative 1 times the bottom to the top row, we get 1, 0, 0. So the first equation tells us that C1 is 0. The second line tells us C2 is 0. The third line tells us C3 is 0. That says the only solution to this system is all the C's being 0. So that says that our set, let's call this set S. So S is linearly independent, which is what we were asked. Let's look at an example where it doesn't turn out to be linearly independent. Well, that's the same question. Let's say we take the set 1, 0, 0, 1, 3, 2. So is this set linearly independent? We start with the same thing. We take C1 times the first vector plus C2 times the second vector plus C3 times the third vector, and we set this equal to 0. And if we write out our system of equations now, we've got our first vector, and then our second vector, our third vector, and then we augment it with the 0 vector. Now this is already in reduced row echelon form. So we see that C3 is free, so that'll get the parameter t. If we take the second equation right here, this says that C2 plus 2C3 equals 0. But this is t, so we get that C2 is negative 2t. And likewise, we have that C1 is negative 3t. So this says we've got this infinite family of solutions right here. So this gives us a non-unique solution. We can have an infinite number of answers for C1, C2, and C3 here. So this says that this set is not linearly independent. And this we'll have a follow-up definition here. A set of vectors that is not linearly independent is said to be linearly dependent. So hopefully that definition is not too deep. If it's not linearly independent, it's linearly dependent. And just like with the span theorem, we've got a theorem about the number of vectors for a linearly independent set. If S is, and let's say that this S is a subset of Rn, if this set is linearly independent, then S has at most n vectors. So if it has too many vectors, some of them are going to be redundant. What if it has fewer than n vectors? Can it be linearly dependent? So let's look at it just to make sure that you don't try to take too much out of this theorem right here. Let's say we have this set of vectors, 1, 0, 1, and 2, 0, 2. Now this only has two vectors, and this is in R3. However, I can take 2 times the first vector and negative 1 times the second vector, and this gives me the 0 vector. So even though we have fewer vectors than the dimension of the space we're in, this is still linearly dependent. All this theorem says is that if you have too many vectors, it can't be linearly independent. So combining these two basic definitions together, we're going to close with the idea of a basis. So a basis for V is a linearly independent spanning set for V. So what this means, it's a spanning set. So any vector in V can be written as a linear combination of our set. And because they're linearly independent, It's not redundant. I don't have more than one way to represent my vectors. And combining those two theorems about the number of bases, the number of vectors in a basis, if you've got too many vectors in your set, it can't be linearly independent. If you have not enough vectors, it can't span. So a basis for Rn must have exactly n vectors. So we'll get into the nitty-gritty of basis in the following section.